First question. So what type of circuit is this, Afroza? Is it an LCR circuit or an RL circuit or an RC circuit? See, this circuit have an inductor, yes, a resistor and a capacitor. So the circuit is LCR. I have muted everyone, just a second. Sorry. Yeah, now you can unmute yourself. Sorry. So the circuit is LCR circuit. You have inductor, you have capacitor, and you have a resistor, L, C, and R. And I connected this inductor, capacitor, and resistor to an AC supply. The AC supply is 20 sine 100t. For inductor, first of all, we will calculate XL, which is known as inductive reactance. For capacitor, we will calculate XC, which is capacitive reactance, and the resistance is R. XL is basically its omega into L. This is your XL, which is omega into L. How much is omega? Omega is this. How much is L? 0.1. So it comes out to be 10 ohm. That is your XL basically. If I want XC, XC is 1 by omega C. How much is omega? 100. How much is C? Capacitor of 1 millifarad. Huh? So C is 1 millifarad. 1 millifarad means 10 raised to the power minus 3. So that comes out to be 10 raised to the power minus 1, which is 10. And your resistor is 10 ohm. So I choose these values so that XL, XC, and XR all comes out to be R, to be 10 ohm. Calculation would be easy. So for impedance, you can use this relation. It's root over XL minus XC square plus R square. This is how we calculate impedance. XL is 10, XC is 10 square plus R is 10 square. So it's root over 10 square, which comes out to be 10 ohm. That is the impedance. No, okay. After impedance, the next thing is the peak value of current. How much is the peak value? Peak value is peak value of EMF divided by the impedance. So the peak value of current is, how much is peak value of EMF? That's 20. How much is the impedance? It's 10. So that's 2 ampere. Similarly, you can calculate the RMS value. It comes out to be I naught by root 2. So the RMS value comes out to be 2 by root 2, which is root 2 ampere. So this is the RMS value of current, which is root 2 ampere. Okay, so we have done LCR circuit. Then after LCR circuit, we did LR circuit. Then we did CR circuit. One last circuit is left, which is combination of inductor and capacitor. The last circuit that is left is the combination of inductor and capacitor, and that's LC circuit. So the next is this LC circuit. So this is your inductor. This is capacitor. Inductance is L. Capacitance is represented by C. This is your AC supply. Current through the AC supply is this. I is I naught sine omega t. Voltage across inductor is this. VL is I naught XL. It's VL naught. VC naught is I naught XC. This is current. In both inductor and capacitor, your current is in same phase. This is I. So in inductor, which quantity leads? In inductor, voltage leads, or that's current which leads? Which quantity leads in inductor? Current or voltage? It's okay. Afroza, Fatma, Fatma, you have attended few lectures of AC. So I hope you understand lead and lag. So do you remember which quantity leads and lag in inductor? Yes, current lags, voltage leads. In capacitor, current leads, voltage lags. This is lead and lag in inductor. I need net EMF or net voltage. Net voltage E naught is the vector sum of V naught L plus V naught C. So to add VL and VC, let's draw this phasor diagram. This is the current, which is I naught. This is I naught. This is phase, which is omega t. This is VL. V naught L. Voltage leads. And current lags, sorry, voltage across capacitor lags by 90 degree. This is V naught C. This is 90 degree, this is 90 degree. So, Fatma, what is the angle between V naught L and V naught C? What is the angle between V naught L and V naught C? I'm putting a vector sign here. 180 degree. So if two vectors are inclined in 180 degree, that means you can subtract them, right? These voltages basically behaves like a vector quantity due to the phase difference. So you can write that net EMF is V naught L, say V naught L is greater than V naught C. So net EMF is V naught L minus V naught C. And this is your net voltage, because if V naught is again, you have two cases. Case one, if voltage across inductor is greater than voltage across capacitor, so that is V naught L minus V naught C. You can write your V naught L as I naught XL, V naught C as I naught XC. This is E naught. You can take your I naught common. This is XL minus XC now. You can write this E naught by I naught as XL minus XC. And this E naught by I naught is basically impedance. Say voltage by current, what is V by I? It's R. For a circuit having only resistor, voltage by current is resistance. For a circuit having net EMF, circuit having inductor and capacitor, the ratio of net EMF and net current is known as impedance Z. So here Z is XL minus XC. This is the impedance of the circuit. This is what we call impedance of the circuit. The SI unit of impedance is ohm. SI unit is ohm. You can also calculate the peak value of current. The peak value of current is E naught by Z, which is E naught by XL minus XC. That is the peak value of current, E naught by Z. Okay, just by looking at this phasor diagram, can you tell me the peak, the phase difference between current and voltage? This is your net voltage. See, voltage is ahead of current. Huh? So here voltage leads current by a phase difference of pi by 2. So if I talk about phase difference, for phase difference, you will write that voltage leads current by phase difference of pi by 2. So if equation of current is this I naught sine omega t, then equation of voltage is this E naught sine omega t plus pi by 2. This is the equation of current and this is the equation of voltage. Current is I naught sine omega t and voltage is E naught sine omega t plus pi by 2. So this is it. That's the phase difference between these two quantities. That was case 1. And we can even calculate one more thing, power factor. Okay, can you calculate the power factor here? See, you have phase difference here pi by 2. The formula of power factor. Power factor is cos pi by 2. That comes out to be 0. If I calculate average power, then average power P average is E RMS, it's I RMS, it's cos pi by 2. Cos pi by 2 is 0. So average power comes out to be 0. So this particular current, which have 0 power dissipation, is basically known as Wattless current. This is known as Wattless current. So the circuit have 0 power dissipation. So the current through a circuit having just inductor and capacitor is Wattless current. Power dissipation is 0. After this, let's move on to case 2. So this is case 2. Afroza, just please unmute yourself and tell me what difference in the calculation are you expecting in case 1 and case 2. Case 1 we have already completed, right? Now in case 2, what difference are you expecting from case 1? All quantities would be same. Let's start from the first quantity, that's E naught. Here E naught is V naught L minus V naught C. So even in this case, the expression of E naught will be same or there will be any difference? So if it is not same, then what is E naught?
V naught C minus V naught L.
V naught C minus V naught. No. V naught C minus V naught. So that is the difference, right? When V naught L was greater than V naught C, I was writing it as V naught L minus V naught C. This is V naught C minus V naught L. So the V naught C minus V naught L will lie in this thing here. It's V naught C minus of V naught L. And this is your E naught. This is it, V naught C minus V naught. And that is the phase difference between them, 90 degrees. So if I want to calculate Z, then instead of XC minus XL minus XC, this will be XC minus XL. Afroza, now tell me, what's the phase difference between net EMF and current? See, in this diagram, it's very clear. This is current I naught. This is EMF E naught. The angle between them is 90 degrees. That means phase difference is pi by 2. Current is ahead of EMF. So you can say that current leads or your EMF lags. So you can write that as EMF lags by current by phase difference of pi by 2. So if the equation of current is I naught sine omega t, tell me the equation of EMF. So, Afroza, this is the statement. This is the equation of current. Can you predict the complete equation of EMF? That will be omega t plus pi by 2 or omega t minus pi by 2. Just tell me either plus pi by 2 or minus pi by 2. Just look at this diagram, study this statement. Good. Minus pi by 2 it lacks. Fatma, you have written the first case, na? Okay. So that is the difference. And if I move on to power factor, the phase difference is 0. So power factor is again, which is cos pi by 2, which is 0. Average power. ERMS, IRMS, cos pi by 2 comes out to be 0. Average power comes out to be 0. Okay, solve this question. An inductor of 0.3 Henry and capacitor of 1 millifarad is connected to AC supply is 20 sine, let's keep it as 100 T volt. Just like the first numerical that we did, first of all, calculate XL. XL is omega L. Omega is 100. L is 0.3, which is 30 ohm. Then calculate XC, which comes out to be 1 by omega C. Omega is 100. C is, it's how much is C? 1 millifarad. 10 raised to the power minus 3. So it comes out to be 10 ohm. Your Z is XL minus XC, 30 minus 10, which comes out to be 20 ohm. Peak value of current I naught is E naught by Z. E naught is 20, Z is 20, it comes out to 1 ampere. After doing LC circuit, the next thing is LC oscillation. In LC circuit, it's basically energy oscillates. Before doing this LC oscillation, let's discuss the oscillation of a spring. Say if you have a spring. Say you have a spring. This spring is at its mean position. The spring is at rest, kinetic energy 0, potential energy 0. I stretch this spring up to an extreme point. Over this point, the spring has some potential energy which is maximum. The kinetic energy of the spring is 0. Once I release this spring starts oscillating. During oscillation, the potential energy of spring get converted into kinetic energy. Because initially, the energy is 0, but when I stretch this spring, the spring just have potential energy. When I release the spring, it keeps on oscillating. Means kinetic energy will convert into potential energy will convert into kinetic energy, and this thing continues. When this spring comes at the mean position, the potential energy comes out to be 0, but kinetic energy is maximum. So during oscillation of spring, there is continuous transfer of energy from potential to kinetic. At some point, kinetic energy is maximum, potential energy is minimum. At another point, potential energy is maximum, kinetic energy is minimum. This energy keeps on oscillating. This is what happens in a spring. Just like the system of spring, if you have an LC circuit, then electrical energy and magnetic energy will oscillate. Here, there is nothing like kinetic energy and potential energy in LC circuit. Instead of kinetic energy and potential energy, here you have magnetic energy and electric energy. The energy oscillates as magnetic energy in inductor and electrical energy in capacitor. The energy keeps on oscillating in LC circuit. So in LC oscillation, it's basically the energy which oscillates. Energy oscillates as magnetic in inductor and electrical in capacitor. So the definition is when a charged capacitor is allowed to discharge through a non-resistive inductor, electrical oscillations of constant amplitude and frequency are obtained, known as LC oscillation. Known as LC oscillation. So the conversion of energy is just like that of a spring. In a spring, potential energy converts into kinetic, kinetic convert into potential. Instead of potential and kinetic, in LC oscillation, magnetic energy converts as electrical, then electrical converts back to magnetic, and it keeps on oscillating. But here, few features of this oscillation is the inductor is non-resistive. Means there is no resistance in the circuit. If there is no resistance, that means there is no wastage of energy in the form of heat. All your energy is conserved. No part of energy is dissipated as heat. So let's take one example, or not just an example, it's a demonstration. I take this capacitor, it's a fully charged capacitor. Upper plate is positively charged, the lower plate is negatively charged. I connected this capacitor to an inductor. The inductance is L. This is the key. Initially, your key is open. Electric charge is maximum. Your capacitor is fully charged. That means your electrical energy is maximum, which is half Q max square by C. Your magnetic energy is 0. UB is 0. And I close the key at t equal to 0. Over t equal to 0 instant, your capacitor is fully charged. Your inductor, there is no current in the circuit, so magnetic energy in the inductor is 0. By UE, I am representing electrical energy. And by UB, I am representing here magnetic energy. So these are the two types of energies, electrical energy and magnetic energy. Next, what will happen? As soon as you close this switch, the capacitor starts discharge. The discharge of capacitor starts. means when the capacitor discharge, current flows from capacitor to the inductor. Capacitor is discharging means charge is flowing through the circuit. Charge flows means there's current in the circuit. Now it's very clear. When the capacitor discharge, charge on the capacitor decrease. That means your electrical energy decrease. Your magnetic energy increase. A time came which is known as T by 4. Capital T is time for one complete oscillation. T by 4 means time for 1/4 oscillation. When this time is equal to T by 4, the capacitor becomes fully discharged. Capacitor is fully discharged, which means all of electrical energy is zero. Now, where is that electrical energy? It gets stored in the form of magnetic energy. Your magnetic energy is maximum, which is half L I max square. Current is maximum. That's why your magnetic energy is maximum. L I max square. Your magnetic energy is maximum, but your electrical energy is zero. So in 1/4 of oscillation, whole of electrical energy get converted into magnetic energy. This is we call 1/4 oscillation. After this, what happened? The process repeat itself. Means from t equal to 0 to t by 4, the electrical energy is converting into magnetic energy. Now the process repeat itself. Means after 1/4 time, like t by 4 time, the magnetic energy start converting into electrical energy. A reverse process. Capacitor starts charging, but it's charging in opposite direction. This is negative, this is positive. Capacitor is charging, that means now magnetic energy is decreasing and electrical energy is increasing. Magnetic energy is converting into electrical energy. Now again a time came which is known as T by 2. Capital T is time for one complete oscillation. T by 2 is time for half oscillation. This electrical magnetic energy converted into electrical energy. Your electrical energy is half Li square, and your magnetic energy is zero. Electrical energy is again maximum. Sorry, it's not half Li square, it's Qx. I'm just writing this is maximum again. Your electrical energy is again maximum. This is basically the half oscillation. This is where the half oscillation completes. So in first fourth oscillation, 1/4 oscillation, electrical energy convert into magnetic energy. In the next 1/4 oscillation, magnetic energy converts into electrical energy. Then you have next 1/4 oscillation, where again the electrical energy, now the time is 3t by 4. Electrical energy again converts into magnetic energy, means you have some magnetic field now. You have some magnetic field now. Your electric energy is absolutely zero, but your magnetic energy is maximum. So again, electrical energy converts into magnetic energy. Then up from next 1/4 cycle. Next 1/4 cycle means T equal to capital T. In T equal to capital T, what happened? The magnetic energy again convert into electrical energy. So your capacitor is fully charged. It is a fully charged capacitor. So your UB is 0. Your UE is maximum again. So if you look at this diagram and this diagram, they are identical. Upper plate is positively charged, fully charged, lower plate is negatively charged. You again get the same state. So that means one oscillation completes it. So during one oscillation, your electrical energy converts into magnetic, then magnetic converts into electrical, then again electrical converts into magnetic, and finally this. This is how where one oscillation is complete. This is known as LC oscillation. So for natural frequency of LC oscillation, I have this inductor. I connected this inductor with a capacitor through a key. Capacity is C, the self-inductance is L. So initially your capacitor is charged. I just closed the key, so some current is flowing through the circuit. So to calculate that natural frequency, there are various ways you can calculate that frequency by conservation of energy, or you can calculate that frequency using Kirchhoff voltage law. So I'm using Kirchhoff voltage law. So using Kirchhoff voltage law, voltage across capacitor plus voltage across inductor is 0. This is KVL, right? The sum of voltages across all elements of the circuit is 0. So if I calculate voltage across capacitor is charge divided by capacity. If I calculate voltage across inductor, it's minus L di over dt is equal to 0. So this is it. Q by C minus L di over dt is equal to 0. That's my first equation. Okay, do you remember any relation between current and charge? Is there any relation between current and charge? Current through the circuit and charge? Current is rate of flow of charge, Fatma. It's minus of dq over dt, right? Though it should be dq by dt, I'm writing the negative sign. It's because the charge over the capacitor is decreasing. Capacitor is discharging. Charge over the capacitor is decreasing. That's why I'm using this negative sign here. So instead of this I can write minus of dq by dt. In this calculation, my aim is to convert the complete equation in terms of charge. So if I do this substitution, you will get q by c minus L d over dt So what do you get? You get q by c, it's minus 9, plus L. See, now you are differentiating q 2 times. One time with respect to time, one more time with respect to time. So that's d square q over dt square is equal to 0. Or you can do one thing, divide both the sides with L. So this is q by Lc plus d square q over dt square is equal to 0. You can simply write this as d square q over dt square plus q by Lc is equal to 0. This is it. Second derivative of charge with respect to time plus q by Lc is 0. Okay, now, do you remember what is SHM? Now I will use some equations of SHM. In simple harmonic motion is a very special type of oscillation. Every oscillation is not simple harmonic. If oscillations satisfy certain conditions, then you would say that oscillation is simple harmonic. And out of those many conditions, one condition is this. If an oscillation satisfies this type of equation number 2, then that oscillation is known as SH. In that particular equation, instead of Q, you can have other quantities depending upon the type of system. Like if I take system of a spring, then instead of charge, you will have X distance. If I take system of a pendulum, then instead of Q, I would have theta, angle theta. If my system is sound wave, then instead of Q, I would have pressure. But here, since charge is oscillating, so I have Q. So the numerator, this is the quantity which is oscillating. Here, charge is oscillating. That's why I'm having a Q here. I'm repeating again. Every oscillation is not SHM. Only those oscillations are considered as SHM which satisfy this type of equation. In this type of equation, the quantity that you are having here or here, like Q here, this is the quantity which change during oscillation of the system. This quantity depends which system are you using. If your system is like in LC circuit, your system is LC, then the quantity is charge. It could even be energy, but I'm writing this in terms of charge only. In a system having a spring, then this quantity is position X. In a system having pendulum, this quantity is angle. So all these quantities change with time. So these are basically the quantities which change with time. Quantities which change with time. Q by LC equals. This is known as second order differential equation of SH. So if you can write this equation for a system, that means that system is in SHM. Of SHM. Now, in this equation, the coefficient of Q, here the coefficient of Q is 1 by LC. This coefficient of Q is basically frequency. This coefficient of Q, 1 by LC, is basically the frequency, omega square. So you can write that your omega is 1 by root over LC. All right, let me add one more step. By comparing with standard equation of SHM, the standard equation is this: d square q over dt square plus omega square q is equal to 0. That is third equation. So this is the standard equation: d square q over dt square plus omega square q equal to 0. Just by comparing 2 and 3, can you tell me what is omega square here? Just by comparing 2 and 3, can you tell me what is omega square here? Very good, Jumana. Fatma, just compare them and tell me how much is omega square. Good. 1 by LC, yeah? Yes. So your omega comes out to be 1 by root over LC. This is the natural angular frequency of LC oscillation. So this is the frequency at which your charge oscillates, or this is the frequency at which your energy oscillates. So if this is angular frequency, you can write this angular frequency as 2 pi nu. So 2 pi nu comes out to be 1 by root over LC. You can write your nu is 1 by 2 pi root over LC. This is not natural, this is not angular, this is linear. So you call this as natural frequency. So always remember, when in question it's written frequency, it's nu. If it is written angular frequency, that means omega. So this is the frequency at which energy oscillates between a capacitor and an inductor. This is the energy of frequency of LC oscillation. In LC oscillation, there is one more thing that you should know, and that is, if I solve this equation 3, I'm writing equation 3, huh? From equation 3, this is equation 3, d square q over dt square plus omega square q is equal to 0. If I solve this equation, you will get that your q is q naught cos omega t plus phi. At this stage, I cannot teach you how to solve this type of differential equation. That's something that you are not expected to learn at this stage. How to solve second order differential equation, no one is going to ask you, at least in physics. Maybe in maths, you have this in your syllabus. But in physics, nobody will ask how to solve this particular equation. But once you have this equation, then you should remember the solution. Solution is this: q is q naught cos omega t plus phi. That is the equation of charge basically. We usually choose t equal to 0. Your capacitor was fully charged. That means your q is equal to q naught. If I substitute all these values here, you will see that q naught is q naught cos omega into 0 plus 1. I'm basically trying to fix the value of this phi naught, phase constant. To fix the value of phase constant, I take this condition. This is known as initial condition. This is known as initial condition. So I'm saying initially your capacitor is fully charged. That's the statement. That initially your capacitor is fully charged. Capacitor is fully charged. That means at t equal to 0, q is equal to maximum q naught. That's it. So if I substitute all things here, you will get q is q naught, not q naught, is q naught cos phi. Q naught will cancel this q naught, right? 1 is cos phi, which means your phi naught is 0. So if you take this condition that initially your capacitor was fully charged, that means your phase constant is 0. You can simply write this equation that if initially capacitor was fully charged, that means your q is your phi naught is 0. Your equation is q naught cos omega t. In majority of books, you will get this equation that your q is q naught cos omega t. If you get this equation, that only means that the author is assuming that initially your capacitor was fully charged. Otherwise, if your capacitor is not fully charged, then phi naught can have any value. But even in NCERT, assume that capacitor is fully charged. So we can work this equation, work with this equation. Q is q naught cos omega. Now, once you have equation of charge, you can write the equation of current. Because current is rate of flow of charge. Then just differentiate your charge with respect to time. You know that current is dq by dt. But instead of dq by dt, I'm using minus of dq by dt. This minus sign simply tells that capacitor is discharging. Charge over the capacitor is decreasing. Minus of d over dt of q naught cos of omega t now. It's minus of q naught d over dt of cos omega t. So your current is minus of q naught. If I differentiate this cos omega t, then its derivative is minus of sine omega t. Along with t, you have this one term omega, so you can multiply with omega here. So your current comes out to be it's q naught omega sine omega t. So this is the equation of current. You can even write this q naught omega as your I naught. This is the peak value of current. Remember this relation. This will be very helpful. So if I write this q naught omega as the peak value of current, then the equation of current comes out to be I is I naught sine omega t. This is the correct equation of current. Okay. After this equation of charge, equation of current, we can even write equations for energy. See, energy here is changing. It's oscillating. The energy, sometimes your magnetic energy is maximum. Sometimes your magnetic energy is zero. That means your magnetic energy is changing with time. Magnetic energy is changing with time. That means your magnetic energy is a function of time. Also, your electrical energy is changing with time, which means your electrical energy is a function of time. So your energy is a function of time. So the next thing that we need to calculate is energy in SHM. Energy in SHM. Not in SHM, basically energy in LC oscillation. Energy in LC. So for energy in LC oscillation, let's calculate electrical energy. Let's first calculate electrical energy. See, your electrical energy is half q square by c. And the equation of charge is q naught cos of omega t square by c. So it comes out to be half, I should write in next line. So your electrical energy basically comes out to be half q naught square cos square omega t by c. That is first equation. That's electrical energy. You can even calculate the magnetic energy. How much is magnetic energy? Magnetic energy is UB, which is half Li square. You can write your I as Q naught omega sine of omega t. Even instead of I, you can substitute these terms. So your magnetic energy comes out to be it's half Li, which is Q naught omega sine omega t square. So your magnetic energy comes out to be half L, it's Q naught square omega square sine square omega t. That is second equation. Basically, both the charges are capital. So I is Q naught omega, half L Q naught omega, half L Q naught square, omega square sine square omega t. So that is the magnetic energy. So this is electrical energy. From these two equations, it's very clear that your electrical energy changes with time, your magnetic energy changes with time. But if you think about the total energy, don't look at the equations, because from these equations you cannot think about the total energy, at least at this stage. Just think logically. Electrical energy is changing. Magnetic energy is changing. Electrical energy is converted into magnetic energy. Magnetic energy is converting into electrical energy. What about the total energy? What do you think? Is total energy changing or total energy is constant? Let's first think logically, then we will try to derive it through calculations, mathematical calculations. Jubana, okay. I got answer from Jubana. Fatima and Afroza. What do you think? The total energy will also change with time, or your total energy will be constant? When I say total energy, that means sum of electrical and magnetic energy. So total energy should remain constant. Total energy is not changing because electrical energy is converting into magnetic. The total energy have both electrical as well as magnetic. Magnetic energy is converting into electrical. So both are basically both are basically changing into another. So total energy will not change. Total energy will remain constant. So if I want to calculate that total energy, the total energy is the sum of electric as well as magnetic energy. Electric energy is half. It's Q naught square by C. It's cos square omega t. This is half L. It's Q naught square omega square sine square omega t. That means the total energy is, okay, let's do one small change here. Just to simplify the calculation, instead of this omega square, I'm writing 1 by LC. This we can use, right? This is the frequency of LC oscillation. This is the formula that we have derived in the last section. Omega is 1 by root over LC. That means your omega square is 1 by LC. So instead of this omega square, if I write 1 by LC, then see the equations are very simple now. It's half Q naught square by C. It's cos square omega t plus half. It's L. Q naught square is 1 by LC. It's sine square omega t. See, this L will cancel this L, and you are left with only, and there is just one more Q naught square. This one. So if I take Q naught square as common, this 2 is common, C is common, you are left with cos square omega t plus sine square omega t, which is 1 basically. So your total energy comes out to be constant. It's not changing. Your total energy is constant. These are basically numericals, conceptual questions that one can ask in LC oscillation. So the next is resonance is series LCR circuit. In physics, whenever you have resonance, resonance means in that system you have two types of frequencies. During resonance, those two frequencies match, they are equal. the result of resonance is the amplitude of oscillation is maximum. This is the entire story of resonance. Whenever you have resonance in a circuit, you have two frequencies. When resonance occurs, those two frequencies are equal. The result of resonance is the amplitude of oscillation is maximum. That is the final result of resonance. So in resonance is series LCR circuit. So this is inductor. This is capacitor. And this is resistor. This is capacitor. This is inductor. This is resistor. And we have connected this through an AC supply. Let's name this AC supply as I is I naught sine of omega t. I is I naught sine of omega t. This is it. So when I say that, so you have two frequencies here. This is one frequency, which is the frequency of your AC supply. Your AC supply, the generator that you have connected with this LCR circuit, this is the frequency of that supply. There is one more frequency. See here, there is this LC circuit. So there is this natural frequency, omega naught, at which the energy is oscillating between inductor and capacitor. So you have two frequencies. The frequency of the supply and the frequency of LC oscillation. If somehow these two frequencies match, means the frequency of LC oscillation and the frequency of supply. If these two frequencies match, then you would say that your system is in resonance. And when your system is in resonance, the current is maximum. Whatever the value of current you are measuring, that value is maximum. If you are measuring the peak value of current, then that peak value is maximum. If you are measuring the RMS value of current, then that RMS value is maximum. If you're measuring the average value, then at resonance, the average value is maximum. So what do you mean by resonance? When frequency of supply match with the frequency match with the natural frequency of LC oscillation, then system is said to be in resonance. Then system is said to be in resonance. If these two frequencies matches, the frequency of the LC oscillation exactly match with the frequency of your external supply, then you would say that your system is in resonance. And what is the consequence of resonance? Due to resonance, current is maximum. At resonance, current is maximum. Current is maximum, that means impedance is minimum. Current is maximum and impedance is minimum. So this is basically the characteristic of resonance. Whenever you have resonance in your circuit, that means the current in the circuit is maximum, but the impedance is minimum. That's resonance actually. So let's start this thing. Now, I have to prove the first statement through second statement. I will use second statement to prove this first statement. It would be better. Okay, just note it down, these two statements, then we'll start the calculation. Using second statement, we will prove the first statement. That current is maximum if omega is equal to the natural frequency. Okay, so to start the equation of this resonance, the calculation of resonance, let's move on to the first numerical. It's an LCR circuit, so the expression of impedance is this, and expression of current is this. So we will start from this equation, these two equations basically. So current in LCR circuit is, this is the expression of current, that your peak value of current is peak value of EMF divided by impedance. So it's peak value of EMF divided by root over its XL minus XC square plus R square. This is the peak value of current. That's E naught by root over XL minus XC square plus R square. Now I need condition when your current is maximum. So your current is maximum if denominator is minimum. For maximum current, because current is inversely proportional to impedance. See, I'm using the second statement that at resonance current is maximum, impedance is minimum. Using this second statement, I will prove the first statement that omega is equal to the natural frequency. For maximum current, Z is minimum. Your current is maximum only if your impedance is minimum. Your impedance is minimum if XL is equal to XC. Because if these two terms are equal, then they get cancelled out. Your impedance is sum of two terms. If one of the term exactly becomes zero, that means your denominator is minimum. It's minimum, that means your current will be maximum. Only Giovanna is left right. Okay, Giovanna, do you understand this thing? This is a statement.
Yes, sir. Understood.
So you can write your XL as omega L, your XC as 1 by omega C. Just multiply with omega here. Your omega square is 1 by LC. Now see, your omega comes out to be 1 by root over LC only. This is what I was writing in statement 1. So statement 2 proves statement 1. That your current in the circuit is maximum only if your frequency is equal to natural frequency. So we write this frequency as the resonance frequency. Resonance angular frequency. So if you want to write resonance frequency, that means it's omega. Sorry, not omega, it's basically 2 pi mu. It's 1 by root over LC. You can simply write your nu naught as 1 by 2 pi root over LC now. This is nu naught. Now, so once you get this resonance frequency, you can calculate the value of current, the value of impedance, the average power factor, everything that we have calculated in LCR circuit. We will calculate all those terms again for LCR circuit, but under this condition. Means at resonance. Now let's first calculate current at resonance. Current at resonance. So at resonance, your current is basically maximum, and that is E naught by R only. It's very clear from this calculation that here this XL will cancel this XC. You are left with only R. So that's why this is E naught. Now I'm taking peak value of current, so I'm writing I naught max. If you say no, I don't need peak value, I need RMS value, okay, fine. Your RMS value will be maximum at resonance. This will be E RMS by R. If someone says no, I don't need RMS value, I need the average value, then take average value. Whatever the value of current you take at resonance, that particular value is maximum. Similarly, you can take impedance at resonance. You can take impedance at resonance. And one more thing, let's plot current versus frequency graph. This is an important graph. So this is your frequency, this is your current. So when your current is equal to this, your frequency is equal to resonance frequency, which is omega naught, your current becomes maximum. I naught is maximum. And this graph should not start with 0. It's not start with 0. This is your current at resonance. Just like current, you can calculate your impedance at resonance. Impedance at resonance. Your impedance is root over XL minus XC square plus R square. So when you have impedance, resonance, this XL is equal to XC, they gets cancelled out. So your impedance is minimum. And that minimum impedance is its root over R square, which is R. So the impedance is sort of minimum, which is equal to R. So this is the minimum impedance for resonance. After impedance, you can also calculate, if I plot this graph, then this is omega, this is impedance. Whenever resonance occurs, the impedance becomes minimum. So this is at a frequency which you call omega naught, and your impedance is minimum. After this thing, you can also calculate the phase difference. Phase difference at resonance. So your phase difference tan phi is XL minus XC divided by R. So at resonance, your XL is equal to XT, that gets cancelled out, your tan phi comes out to be 0. When your tan phi comes out to be 0, that means your phi comes out to be 90 degree. So phase difference is 90 degree. Tan phi is 0, that means your phi is 0 degree. I'm sorry, tan 0 is 0, so it's phi is 0. If I calculate power factor, that means your cos 0, it's plus 1. Your power factor is maximum. After power factor, you can also calculate average power. Average power. So your average power comes out to be ERMS, IRMS, cos 0. This is ERMS into IRMS. Your average power is maximum. So during resonance or at the resonance frequency, your LCR circuit behaves like a circuit having resistor only. So at resonance, LCR circuit behave like circuit having resistor only. It behaves like a circuit having resistor. This is the one of the characteristic of resonance. LCR circuit behaves like a circuit having resistor only.